So this is our EDAS dashboard project, which is built on STM32 F103C86 Blue Pill, and it is stimulated in Pixim Lab with a live Python dashboard. So I am Mamalapalli Jahnavi, and I would like to thank my mentor Sneha and also the emertxe team, including throughout their guidance through this internship. So let us see the problem and the solution. So what is the problem? So modern EV generates huge volumes of sensor data, speed, SOC, motor temperature, torque, range, and with no single use to monitor performance and safety together. Our system solves this real-time speed, SOC, range monitoring. So EDAS collision blind spot detection, motor fault alerting, a live Python dashboard over UART, and a child alert system and a drive mode control. Let us see the system architecture overview. So data flows from the simulated sensors to potentiometers for accelerator, brake temperature into STM32 Blue Pill, running our EV control EDAS engine and fault handler. So that's transmitted over UART at 115200 pps as structured telemetry frames and rendered live in our Python matplotlib dashboard. So real industry versus our project. So how it works in real industry and our project. So we map every EV component in our simulation. Potentiometer stand in for pressure proximity sensors. The Blue Pill acts as our ECU, which is electronic control unit, and UART replaces CAN, and our Python dashboard mirrors and industrial instrument clusters. So let us see what are the phases I have gone through this internship. So we have gone to the 9 phases from development and birth setup through GPIO, ADC, EV dynamics, ultrasonic EDAS, fault handling, UART telemetry, UART shell, and finally Python dashboard. So let us the tools used for this. Used for this STM32 Cube IDE for firmware, Pixim Lab to simulate Blue Pill, Python 3 with MATLAB, NumPy, PySerial for dashboard. On the peripheral side, we have configured timer 1 for 10 minutes EV tick and timer 3 for 100 sensor reads, timer 2 for ultrasonic echo capture, timer for PW from buzzer, ADC channels, PA2 for the potentiometers, and the USAT 1 and PA9 talking to Pixim virtual comport at 1150-100 baud. So let us see the ADC versus EV dynamics. So this phase started about 12 ADC conversion, reading PA0 for accelerator, PA1 for brake, PA2 for building the EV, and dynamics engine itself. So motor torque from 0 to 250 nanometer, etc. These are done in the ADC and the EV dynamics. Let us see the fault detection and altering system. So we used a bit fault register, a single byte where each bit represents a different fault over temperature, low SOC, critical collision, sensor timeout, communication timeout, and etc. And UART telemetry protocol. Every 100 milliseconds we transfer to ASCII frames over UART. Line 1 carries EV data like speed, SOC, torque, temperature, range. Line 2 carries EDAS data like sensor distances, time to collision, collision level, and fault byte in hex. Let us see the UART shell. So we also built a UART shell so that we could test domestically without touching physical potentiometers, such as commands like speed, SOC, temperature, mode, fault, reset, status, etc. Use it directly and validate alarm thresholds on demand. Let us finally see the Python dashboard. So finally the Python side, a circular speedometer gauge that shifts color from green to red, a live SOC bar with drive model label, a 60 sample rolling speed chart, and info panel, top down EDAS, birds view, etc. Shows us the distracted obstacles. So this is our project and our workflow, and this is the workflow. First we have built the real-time speed analysis, next ADS, collision detection, blind spot monitoring, motor over the temperature fault, etc. So let us walk through the running. So let us see the working. So let's start with the project structure in STM Cube IDE. The firmware is organized into a clean modular files. This separation makes the system easier to debug, test, and extend. So main.c handles the system initialization, and main control sensor module manages HCSR for ultrasonic sensor readings and ADC based analog inputs, and the fault management handles error detection and fault codes across the system, and the buzzer drives our audio alert output, and a UART command shell that let us interact each system in real life from serial terminal. Each EDAS features collision warning, blind spot detection, overspeed error is built at its own function block, so the logic stays readable and testable. So this is the pin configuration. We can see how we configured this, and in cock configuration also we need to set things. So these are the system core, analog timers, etc. So here we have made some changes in the clock configuration. We need to select HSA, etc. So let us see the firmware logic walkthrough. So let us look at the actual detection logic works. For forward collision warning, the HC ultrasonic sensor continuously measures the distance to the obstacle ahead. When the distance drops below a safety threshold, the system triggers a warning stage, activating the buzzer and flagging a warning on the dashboard's output. So blind spot detection works on same ultrasonic sensing principle but monitors the side zones, altering the driver if a vehicle or obstacle is detected in the blind spot, while a large change might occur. So overspeed detection reads analog input through the ADC, simulating a speed sensor, and compares it against the configurable speed limit, crosses that limit, and the system raises an overspeed alert. So underneath all of this sits a fault management module, which continuously checks the sensor health and system status, logging fault codes if any subsystem like sensor timeout or an outrange reading misbehaves. This is what makes the system genuinely ADAS-like rather than just a sensor demo. It's aware of its own failures. So let us see the stimulation setup for PixSim Lab. Since we don't have a physical hardware for this capstone, the entire board is simulated using PixSim Lab, running our compiled STM Firm32 exactly at IO2 on a real silicon. Here you can see a virtual STM32 F103CA T6 blue pill board, wired up with ultrasonic sensor and AD input components. One important fix during the development was correcting oscillator configuration, switching the HSI to HSC. Since the simulator does not emulate an external crystal the same way real hardware does, so that one change was the key to getting stable timing and working UART communication in stimulation. So for serial communication, I used a COM-port pair setup through COMCOM, paired with ESP for managing the viral serial connection, so the microcontroller's UART's output could be routed straight into the straight term on the PC. As you can see, now we have opened the VPSC. Here we have connected COM1 and COM2 pairs. And the Python dashboard. As you can see, the electronic vehicle is near to the obstacle. It shows the alarm as first advisory. When it goes very near, it shows it is critical. So first one is the forward collection, and I have said, and next the blind spot detection. It's the same principle, sight phone sensor, and you can see the warning red flag appears the moment an object enters that zone. So the overspeed alert as I increase the simulated analog input representing the vehicle. The ADC reading climbs, and once it crosses over the configure limit, the system flags an overspeed condition. And finally, so the fault condition to show the fault manager system catching an abnormal sensor state and logging it rather than the system silently falling. So that covers the core of the EDS EDAS dashboard: forward collision warning, blind spot detection, overspeed alerts, and fault management systems, all running as modular embedded C firmware on STM32 F103C8D6, valid through Pixim Lab simulation and monitor live over UART via Telegram. This project brought together embedded C development, sensor interfacing, real monitoring, and stimulation-based validation. The same skill set used in automotive real ADAS development, just scaled down a bit to Bluepill and a simulator. Thanks for watching.